Yes, I welcome you all for another beautiful presentation on random variables and random processes. In this, we will see our subtopic as joint probability distribution as well as joint probability density function. So these are the very important and very beautiful topics under random variables and then random processes, right? In previous presentations, we have seen what is a distribution function and what is a density function we have seen. By the way, this is our lecture number 6, right? Okay, if you consider any random variable capital X, for example, and so and if you define it's it is like this as an event for any random variable X, if this random variable is defined in such a way that in this formation, then this is called an event. This is we have seen already. This is called an event. And if you obtain or if you want to calculate the probability of this event, that is nothing but probability of capital X is less than or equal to small x. This is nothing but means that the probability of an event, this is called an event. For this event we want to determine the probability, that is probability of an event is called a function, that is called a distribution function, that is denoted by capital F of X. This is already we have discussed in our previous presentations. Clear? So this is what the probability distribution function with respect to single random variable capital X. Whereas in the bracket, if you see this, this is the possible outcome value of capital random variable. Means it is the possible outcome value of random variable X. Right? What I mean to say is that the probability of any event is called the probability distribution function, and it also called as a cumulative distribution function. This is called your PDF. PDF means probability distribution function, or also called as CDF, that is cumulative distribution function with respect to a single random variable, right? Similarly, what is the density function? Density function is nothing but the derivative of the distribution function. Once if you know the distribution function, then if you take the derivative of this, then obviously density function will be obtained. That means that actually, so the density function is nothing but, so this is what we have seen now. The probability distribution means your capital F of X is equal to probability of capital X is less than or equal to small x. This is called a distribution function, right? With respect to a single random variable X. So now what I want to define is that I want to define another definition, that is probability density function. Probability density function, and remember that this is always denoted by capital PDF, whereas the small, this is density function, is denoted by or can be represented by small PDF. Remember that there is a little bit difference between PDF and then capital PDF and then small PDF. The small PDF is used for density function, whereas capital PDF is used for distribution function, right? So now this is what your capital PDF actually, it is capital PDF, or also called as your CDF, cumulative distribution function. Remember that. So PDF is equal to capital F of x. Now I want to define from this the another function. It is called the density function. This is distribution function. Now the density function is nothing but small f of x. Small f of x. Remember that it is a small f of x. So small f of x is nothing but the derivative of distribution function, means d by dx of your distribution function. If you take the derivative of the distribution function, so this is the distribution function actually. If you take the derivative of the distribution function with respect to dx, and that derivative of distribution is nothing but your small f of x, which is called probability density function. This is called probability. This is called your small PDF. Small PDF. Remember that. PDF. It is a density function with respect to random variable x. With respect to random variable x, capital X. This is what the basic definition of a distribution function as well as the definition of a density function with respect to single random variables, right? Okay, this is what with respect to a single random variable. Now in this presentation, just I would like to give you little bit extension to this single distribution function as well as the single density function. The extension is nothing but sometimes it is required to consider two random variables instead of one random variable. So this is all about with respect to single random variable, right? So with respect to single random variable, the corresponding, this is the distribution function. With respect to single random variable x, this is the density function. Sometimes it is required to consider two random variables. Okay, so two random variables will be given, and for that with respect to those two random variables, we need to find out the distribution function as well as the density function. That is what the subtopic of our today's, right? So now let us consider two random variables, two different random variables x and y. Then what is their corresponding distribution function and corresponding density function? How they look like, that we will see now. Let us consider, so for your okay, let us consider, right? Let us consider two random variables. I can simply write RVs, means random variables. Let us consider two random variables, that has capital X and then capital Y. Okay, then correspondingly with respect to random variable x, what is the distribution function? This is nothing but f x of x is its distribution function, and corresponding y, what is the distribution function? It is capital Y of small y, definitely clear. And further, this fx of x is nothing but, tell me, it is probability of capital X is less than or equal to small x, is it not? And your f of y is nothing but what? It is probability of capital Y is less than or equal to small y. What I mean to say is that I am considering two random variables x and y. X and y. X and y are the two random variables. Okay, then with respect to x, individually f of x is its probability distribution function, and this can also be defined as like this, probability of an event. Similarly for random variable y, this is the distribution function with respect to random variable y, and this is corresponding its probability. Now what is the distribution function with respect to both x and y? These are the individual actually. Now what is the distribution function with respect to x and y? Is called the joint distribution function. So if you consider with respect to these two x plus y, let us say, then that is called joint distribution. that is called joint distribution. That is called joint distribution, and that is given as capital F of x comma y. In bracket you can write small x and small y. That is denoted by like this, or you can write capital F. In suffixes you can write x comma y, or sometimes you can simply write f of xy also, nothing wrong in that. You can put either comma as I have shown here, or simply you can write fxy without comma also. Therefore both are same, both are gives the same meaning, nothing wrong in that. Either you can write f of xy in this form, or you can write in this form. This is what the joint distribution function. Well, now how that further can be explained as the joint distribution function. Clear? So the joint distribution function I have given you that. So that is what f of x comma y, let us say in bracket small x comma y, and this is equal to probability of, you can write like this, x is less than or equal to small x, and comma capital Y is less than or equal to small y, means probability of those events actually. Is it not? If you write, this is what the definition of a joint distribution function, nothing but. So for single random variable, we know that fx of x is equal to probability of a single event, that is x is less than or equal to x. This is the single event. For the single event we are taking the probability, therefore probability of an event nothing but distribution function. But in this case we are considering the joint probability distribution function. Joint in the sense we have to consider the events of both the random variables. So this is the event of the random variable x, and this is the event of random variable y, and this is called the joint event actually, probability of the joint event. Therefore this is called the joint distribution function. This is called the joint distribution function. So if it is asked in the examination, then you need to give this expression. This is the expression for joint distribution function. F of xy of xy is equal to probability of capital X is less than or equal to x, comma capital Y is less than or equal to y. Right? So this is what. Say for example, so this can be extended to any number of random variables. So here, for example, I have considered two random variables x and y, and you can extend this for any number of random variables. N number of random variables also you can expand actually. Right? Now let us see what are the few properties of this joint distribution function. And even before going to that, at this instant of time, I can give the definition of the joint PDF also. This is what joint probability distribution function, joint PDF, you can say capital PDF. Now if you say the small f of xy is nothing but joint probability density function, that is nothing but joint probability density function, means small PDF, that is nothing but small f of xy comma xy. So what is this? This is nothing but, so in single random variable case what we have seen, it is the derivative of the distribution function d by dx of capital F of x. But here we are considering two random variables, therefore you must have the derivative actually. It is nothing but, in this case we will consider actually the partial differentiation, dou by dou x into dou by dou y, is it not, of capital F of x comma y and then x comma y. This is what actually the definition of your small f of x means, small PDF, probability density function, Therefore dou into dou square, is it not? So it is given as small f of x comma y of x comma y This is equal to, furtherly this can be given as dou square by dou x into dou y. You can write like this, dou square by dou x into dou y of f of capital F of x comma y and small x y. Okay, you can close the bracket like this. This is the definition of a giant PDF. This is the definition of a giant PDF. Clear? This is the definition of a giant PDF. So these are the definitions of a giant distribution function and then giant density function. Well, these are the definitions. I think you understood well. I hope that you are following this, and I think I will finish off this presentation with the definitions of this probability distribution function as well as the probability density function, and in the subsequent presentation we will see the very important properties of distribution function as well as the density function, and thereby we will solve some little bit important examples on this, and we will see the extension part of the distribution function, density functions in the coming subsequent presentations. I hope you understood well, and thanks for watching, and we'll meet in the next presentation. Have a beautiful day.